Hello everyone, and welcome to the Game Engine programming series where we write a game engine from scratch. In the previous episode, we made ourselves a nice little class that can be used to upload data to the GPU. This data can then be accessed only by the GPU. We also started working on uploading geometry data using this class, where we wrote a function that uses the createBufferHelper function to create a buffer resource that contains the mesh data. As we saw in the last video, the pointers to the buffers are put in a free list, which is just a flat list of items. This means that we need to implement some data structure that contains information about the LODs and the submeshes within each LOD. This episode is about setting up this data structure and finishing the functionality for uploading geometry assets to the GPU. Before we start, I need to fix a couple of typos and do some improvements of the code from the last video. For some reason, I made an unusual number of mistakes, which I did annotate in the video, so if you paid attention to those, you should be good. However, I do need to fix those mistakes before we can continue. Let's start in the upload context and add an assertion to make sure that an upload context should be done uploading before it's destructed. I'll also make these accessors non-discardable to avoid certain types of bugs. In addition, the upload context class should only be used when the command queue is initialized, so I'll add an assertion for that here as well. In the last video, I made two separate data structures to hold vertex positions and vertex elements. I think that merging the two structures will result in simpler code, and that's why I'll make one structure that contains everything. On the other hand, some render passes like zPrepass and ShadowPass only need to refer to the index and position buffers, so I might revert this change in the future. But for now, I'm choosing for the simpler code. So I'll rename the structure to submeshView. Get rid of these comments because this function only looks at one submesh at a time. I'll move this block of code up and change the names accordingly. And I update the remove function as well. If we look at the data format, we see that the index count is the third integer and comes after vertex count. However, I'm reading it after primitive topology, which is wrong, so we need to move it up a little. I also used a 16-byte alignment instead of 4, and although that would also work fine, it's better for data sizes to use a smaller alignment. And we use this D3D12 constant for the alignment, which is defined to have a value of 4. To calculate the index buffer size, we need to use the index count, not the vertex count. And in the index buffer view, we need to use index buffer size, not the position buffer size. That's hopefully all for this function. Next, I'd like to improve the descriptions of these alignment functions. And that's all I wanted to fix for now. If you encounter any issues that I missed, always feel free to point them out in the comments or on our Discord server. Okay, let's continue by writing a function that takes a block of memory and creates a resource in a format that can be used by the engine. We also need to tell this function what kind of asset it should expect in the block of memory. So I'll use the same enumeration for the asset types as the one we defined a while back in the editor. We'll also need a function that removes these resources from the engine. Let's add a CPP file for the function implementations. Here I use a switch statement to call a creation function for each type of asset that we want to create. At this point in the series, we only have geometry data, so I'll write a function that creates a geometry resource. We do the same thing for destroy resource function, except now for each asset type, we call a function that destroys that type of resource. In order to implement the create geometry resource function, we again need to define the format of our data. We already know that it must contain submeshes, so we can get that part from submesh add function in the low-level renderer. The hierarchy of LODs and submeshes is not API specific, and that's why we are going to keep that information here, where we don't have any notion of platforms and APIs. Since this data must contain every bit of information about a complete geometry asset, we can simply name things that describe such an asset. Let's start with the number of LODs. We need to know at what threshold we should switch between LODs, so we put LOD threshold next, followed by the number of submeshes for each LOD. Remember that each LOD has one or more submeshes. Because we are only interested in the geometry hierarchy and not the content of submeshes, we need to be able to skip over submesh data without having to read them, and that's what size of submeshes is for. It's the total size of submeshes in each LOD. As I mentioned, an LOD has one or more submeshes, so the data contains an array of submeshes with the number of elements given by submesh count. And finally, we have our array of LODs, because each geometry has one or more LODs as given by the value of LOD count. Now I'd like to extract the hierarchy and process it in such a way that it would be quick to look up what submeshes need to be rendered for a particular geometry and a specific LOD. So we need to define an output data format that we can use for that purpose. Obviously, we need to remember how many LODs there are. Next, we put the thresholds for each LOD in an array. Because all submeshes that we upload to the low-level renderer will end up in a flat list, we remember the offset at which submesh IDs for an LOD start and the number of submeshes for that LOD. Lastly, we put all IDs of submeshes that are loaded onto the GPU in an array. Now, how do we intend to save this information? Note that each geometry asset could have a different number of LODs and submeshes within those LODs. The approach that most people would normally take is to use dynamic arrays, also known as vectors, to put thresholds, LOD offsets, and the GPU IDs in and use another vector for all geometry hierarchies. Although that's a fine approach and it's also reasonably simple to implement, it will allocate chunks of memory all over the place, and that's exactly something that CPU caches aren't particularly fond of. So what I'd like to do is to allocate just one block of memory with the appropriate size for each geometry hierarchy and write this data to the allocated memory. Then we put pointers to each memory block in a free list. Now let's write a function that creates a block of memory that contains such a hierarchy. In order to make it easier for us to read and write data to raw memory, I'm going to create an internal class that's very similar to our blob stream reader and writer classes, but it's specific for our output hierarchy format. It's also used exclusively as an internal class, and no one else needs to know about it. So please don't tell anyone that we did this, okay? This is again a class that we only want to use locally, and it can't be moved or copied. We also need an additional struct for formatting LOD offsets. The constructor accepts a buffer to read from or write to, and an optional parameter for the number of LODs. The class keeps a pointer to the buffer, but we also need to add pointers to the data within this buffer. Specifically, we need pointers to the array of thresholds, the array of LOD offsets, and the array of GPU IDs. Finally, we also remember the number of LODs. Going back to the constructor, we need to write the number of LODs to the start of the buffer. This is only needed if we are initializing the buffer with hierarchy data. In that case, the optional LOD parameter contains a valid value. Next, we initialize the LOD count with number of LODs and set the pointers to the correct offsets within the buffer. First, the thresholds pointer points to an offset after the LOD count. Then we have the LOD offsets pointer, which points to an address after the last element of thresholds array. And finally, the GPU IDs pointer that points to a location after the last element of LOD offsets array. After initializing this class, it's not trivial to get the GPU IDs for a particular LOD. We can just point to an element within the array of GPU IDs using LOD offsets and count. We can also determine the LOD index given a specific threshold. Let's finish the class by writing some accessor functions. Now we can use this class to actually create a block of memory that contains geometry hierarchy. Of course, before allocating a block of memory, we need to figure out how big it should be. Therefore, I'm gonna write yet another function that calculates this size by going through the data and see how many LODs and submeshes we have. Let's use our beloved blob stream reader to easily examine the data. The first item should be the number of LODs, which we can read as a 32-bit unsigned integer. We know that we need room to put in the LOD count, LOD thresholds, and LOD offsets, so we can already add those up together. Next, we calculate the total number of submeshes that will result in the same number of GPU IDs. So for each LOD, we skip over threshold value and read the number of submeshes, and then add the size that's needed to hold that many GPU IDs to the total size. Finally, we jump over the actual mesh data because we don't care about those in this module. Now that we have the size of our memory block, we can allocate it and fill it in using the geometry hierarchy stream class. To read the geometry information from the data parameter, I'm going to use the blob stream reader again. First, we read the number of LODs and create an instance of geometry hierarchy stream for the allocated buffer. We also pass the number of LODs to the constructor, which will write it to the buffer. Then we loop through the LODs, and for each one we write the threshold value to the corresponding item in the hierarchy thresholds array. Next, we read the submesh count, which will be the same as the GPU ID count, and use it to fill in the LOD offsets. We don't need to read the size of submeshes and we can skip it. Now for each submesh, we remember our read position within the buffer and call the renderer's addSubmesh function to upload it to the GPU. Obviously, I need to add that function to the renderer's interface, but it effectively calls this add function, which we wrote in the previous video. It will read the submesh data, upload it to the GPU, and advance the data pointer by the number of bytes that it read from the buffer. That's why we need to skip those bytes to go to the next submesh. Finally, we add the buffer pointer to the free list of geometry hierarchy pointers and return its ID. Again, because we can create resources asynchronously, we need to lock our data to avoid race conditions. Therefore, I'm going to add a mutex and use it to lock the free list whenever we need to modify it. Before we continue, I'd like to write an assertion to make sure that all threshold values are in an ascending order. This is a lambda expression which returns true or false depending on whether our test passed or not. Let's add this function to the renderer's interface next. Here I'll declare a function that adds a submesh to the renderer and another one that will remove it. For the implementation, we need to expand the renderer's interface by adding two new function pointers with the same signature. Then we can use them to point to the low-level implementation that's API specific. That's it for creating a geometry hierarchy. I'll write destroy geometry resource function next. Here we basically just want to free the allocated block of memory, but before doing so, we must also unload all submeshes from the GPU. So we need to go through all GPU IDs and call renderer's remove submesh to unload those resources. To do this, we can use the geometry hierarchy stream and iterate through LODs and use LOD offsets to access each item in GPU IDs and remove the associated buffer resource from the GPU. When we are done, we can free the memory and remove this pointer from the free list. I think this is a good place to leave it for today. Next time, we are going to improve the way we remember our geometry hierarchy for geometry assets that only have a single LOD with a single submesh. We are also going to use this pipeline to officially upload our first 3D model to the GPU. Hopefully you enjoyed watching this video, and as always, thank you so much for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!